Efficient prices in a dynamic context. Economics' current notions about efficient prices all subsume references to an equilibrium state upheld by optimality. Possibilities for artificial economic calculation are then confounded by a further consensus that the real economy is never in equilibrium, which is observably true. Our own discussion of equilibrium goes even further, expressing a conviction that equilibrium not only does not exist, but that, even if it did exist, references to equilibrium cannot be a viable element in any theory about a dynamic process. The only prices that can exist are those operating in a given moment. So the prices that might guide economic processes into a stable optimum are never really known, and must be ascribed to economics' great deus ex machina, the inscrutable yet omnipotent market. This video is SF Econ's heresy against that deity. As we begin, please be advised that the pricing mechanism examined here is somewhat more primitive than the one to be revealed through a detailed study of SF Econ's Model 0. Having been chosen for its illustrative simplicity, this price formulation is operative only for a hypothetical economic system that is altogether isolated from foreign trade. It also elides calculations of the absolute commodity values that underlie more complex models, and it ignores certain specifics about household sectors that will be discovered by those who make closer studies of our theory. Our discussions of Hayek's knowledge problem laid down a marker to the effect that the shapes of production and utility functions provide all that is required for price calculations that are operative in a dynamic context. We are here to redeem that marker. As preparation for this exercise, please give some consideration to the knowledge brought together in formulating a functional relation between an output rate and its factor inputs. Here we have an awareness of not just one sector's technology, but of how it fits in with the technologies of all the other sectors that produce its productive factors. Surely this interlocking of technologies portrays considerations of the mutually optimal value system through which they are related. Our discussion of the polynomial factoring problem formulated a parameter zeta that brought together information given to the factoring problem. That is, utility parameters ZU and prices pi p. This discussion turns on another parameter, beta, that brings ZU together with the physical state variables YE, described in our video on the material circuit, and with the sector's financial states epsilon, developed in our video on the financial circuit. While not at all obvious at first glance, each sector I's zeta and beta would compute to exactly the same value if the economy were ever to actually achieve the mythical state of optimal equilibrium. Such a state would be expressed in cell-for-cell equality between the matrix of optimal asset usage rates Q sub ij and the actual asset employments E sub ij. The point in having two distinct approaches to a single quantum, even one that is ultimately unknown, is for each to supply data required by the other, and thereby establish a dialectic through which they proceed toward unity, their unity being coterminous with economic optimality itself. Video media do not lend themselves to the lengthy algebraic development needed to prove the identity between zeta and beta. So we will task the auditor to independently study the materials relevant to this matter that you will find referenced for you in the show notes. The sector's zeta parameters determine optimal rates Q sub ij for sector I to use good J. And, as described in our video on the material circuit, the sector's Q sub ij's add up to the total domestic demand for a good J. These elements of demand condition the replenishment rates R sub ij that continuously drive the expenditure E sub ij of physical assets. Replenishment rates R sub ij also combine with prices P sub j, to create net cash flows rho sub I that drive the financial circuit and create the sector's financial states epsilon sub I. Prices were considered known throughout our presentation of the factoring problem and in developing the material and financial circuits. These developments produced rates rho R that were numerically integrated over time to create the current state variables epsilon E, which then determine the sector's current betas. Beta, because it was formulated in terms of variables that are integrated functions of prices, can be used for price determinations without creating direct circular references. These determinations begin by rearranging the equation for Q sub ij at the upper left into the equation below it. We then substitute indicia of the system's current state for corresponding elements of the state that would be optimal at current prices. Beta sub I replaces zeta sub I. E sub ij replaces Q sub ij, and our prospective marginal value of good J to sector I, P sub ij, replaces J's current price, P sub j. Our pricing mechanism's dynamics can be envisioned in a hypothetical space defined by the value equation's numerator beta sub I and its denominator U sub ij plus E sub ij. Here we can see that a given sector I's marginal value of J presents a discrete point in this contrived space. If we then proceed to record the marginal values of J for all of the sectors I to which J is input, we arrive at a visualization of all the data pertinent to a general consensus of J's current value throughout the entire economy. We then erect a gradient from the origin to express the best visual fit to these data, and label the slope of this array as J's prospective price P sub j. We say prospective because P sub j is not yet fully developed. At this point, P sub j only carries some sort of a weighted average of the sector's current marginal values of J. Basing this consensus on best visual fit gives the greater weight to data points that are furthest from the origin, which is to say those sectors with the greatest financial heft, as indicated by their larger financial state variables, epsilon. Beyond that, the mathematical formalities to be used in establishing this best visual fit remain open to specification. Ordinary least squares suggests itself for this role, but it is not really appropriate. 1. Because elements of the abscissa are not known with precision, and 2. Vertical errors are not what we wish to minimize, so much as errors that are orthogonal to the central trend line. SF Econ's current method for drawing P sub j out from among these data is simply to add all the numerators of the marginal value equations together, and to divide that sum by the sum of all the denominators. This ratio sum technique has proven effective in our modeling, and though it is obviously quite simple, it does entail a pleasing degree of mathematical sophistication. The reasoning behind our technique is, however, another of those purely mathematical developments that do not lend themselves to transmission through video media. References provided in the show notes will guide the auditor to supporting material in the form of HTML presentations. Our equation for the consensus marginal value of a good J can be readily transformed to represent the more familiar notion of the demand schedule. Substituting the abstract quantity of prospective demand D sub j for the sum of the sector's current actual employment rates E sub ij creates a functional relation between price and demand. And this equation maps neatly into the dimensions of price and volume. From here we proceed upon a fundamental definition of the market as continuously reformulating a price such that everything currently being supplied will be demanded. Our treatment of the material circuit established that the model's operation continuously recomputes elements of supply, which is to say market levels and output rates. Entering current supply, S sub j, upon the abscissa of our demand schedule allows us to read J's market clearing price off the ordinate. This operation can be reduced to an equation derived by simply substituting supply S sub j for demand D sub j in our demand schedule. With SF-Econ's price equation finally before us, we can close with some commentary on the meaning it contains. First, we must allow that these are essentially Say's law prices, and we must then acknowledge that many established lines of economic thought emerge from the premise that Say was wrong in asserting that supply will create its own demand by downward pressure on prices. Here we have another topic that is too broad and diverse to be usefully addressed in a video, so once again the auditor is directed to the show notes for references to SF-Econ's take on this controversy. Secondly, the auditor should consider that everything composing our price calculation is a variable, except, that is, for the production and utility parameters, which are open to exogenous respecification at any time. Prices are a thing of the moment, and our demand schedule is not a boundary condition, but the composite of instantaneously computed variables that are in constant flux. A third aspect of SF-Econ's price computation is revealed by further consideration of the beta sum in its numerator. Examining the makeup of a given sector's beta sub I, we see that it brings together everything about a sector I's production parameters ZU, as well as everything about its current financial and physical state epsilon E. Thus the sum of all the economy's betas brings in all of the sector's current boundary conditions, together with all current values of their state variables. Every price computation has the same numerator, and every price computation references substantially the same information, which is everything pertinent to any of the sectors. The sole aspect of the economy's current state not present in the sum of all betas is of course the market levels, and these are brought in through the supply rates S sub j. There is nothing in the SF-Econ models that is not expressed through their price calculations.